All right, in this video, we're going to revisit some applications we saw in Calc 1, but now being able to extend on into some higher dimensional stuff. So before I get too far ahead of myself, if it's been a while since you've talked about these types of things like moment, lamina, density, center of mass, and centroid, I would encourage you to go ahead and go back into my Calc 1 channel. It's, I believe, the very last video titled Centroids. And just watch maybe the first bit where I redefine what these things are. I'll talk about them as I go through this video, but I'm not going to redefine them since it's the exact same stuff from Calc 1 and it's all defined in this video here. So the thing that we're going to move into now is going to be finding these centroids. Centroid is the center of mass for a homogeneous lamina. So a centroid is a center of mass, kind of like the balancing point, if you will, for a homogeneous lamina. And a lamina is that thin plate, and the fact that it's going to have constant density means that it's homogeneous. So these are the formulas that we're going to use if we're dealing with x's and y's. You've got the x bar and y bar, and then x, y, and z, you'd have the x, y, and z bar. One of the interesting takeaways from all of this is this guy right here. If you've got a triple integral, well, let's go back here. If you've got a double integral over a region, you've got a function here, we know that one of the translations could just be volume. However, when you go up to triple integral and you have a function here, many times it's a little confusing. What are we finding, right? We're in a higher dimension. What is it we're dealing with? Well, provided that this is a density function, then the overall outcome could be mass. And so that's a kind of a fun takeaway from what we've been studying so far. So regardless, if this is going to be your mass, then your x bar and y bar will be 1 over the mass, and then this thing right here. Alone, without the 1 over m, alone, just this stuff right here, the x bar and y bar, these are going to be the moments about the coordinate planes. If you remember, a moment is the tendency for mass to produce rotation at a given point. So combining it with the 1 over m, though, that is going to give us the coordinates for our centroid, or our center of mass, depending on what's being asked. And so when it comes to x bar, y bar, z bar, you'll see it's the exact same setup. You've got the 1 over mass out in front, followed by very similar formulas. Without the 1 over m, again, this is going to be the moments. The moment would be the coordinate axes, of course, and the moment, again, tendency for mass to produce rotation at a given point. So let's go ahead and take a look at how to come up with these types of things depending on different problems. It'll be very similar to what you saw in Calc 1, only now we have multiple integrals. All right, so in the first example, we're going to find the centroid where r is bounded by the coordinate axes, and then x plus y equals a bigger 0, with a density function of x squared plus y squared. So to get this thing going, first things first, to find x bar and y bar, you're going to need 1 over m. So let's start with m. M is going to be that double integral, and then we just drop in the density function, x squared plus y squared there. And then our focus is solely upon the dy dx or dx dy and the bounds. So let's take a look now and see what this gives us with. So if we're given that we're in the first, the coordinate axes, and that line that I'm talking about is y equals a minus x, that's going to give us this region right here that we need to focus on. All right, so if we essentially do this the same way we would have in earlier problems, maybe I would look at this vertically, and that tells me then I would go a dy dx. My top part would be the a minus x. My top part's the line, a minus x. So I'll write that in there, a minus x. The bottom part would be 0. And of course, I would move from 0 to a. This intercept right here is a. If we let y equal 0, you can see x would equal a. So this thing right here gives us a final answer of a to the 4th over 6. And remember, that's going to be the mass. So for x bar, that's going to be 1 over the mass. So 6 over a to the 4th, double integral, Now for x bar, we put an x in there along with the density function. Now conveniently, we spent most of our time talking about these red bounds. Once you come up with them once, it's going to be the same for all of them, which tells us that this is going to be a dy dx, and we would go from 0 to a minus x and 0 to a. This would give us then a 2a over 5. Similar for the y bar. We'd have 6 over a to the 4th. That's the 1 over the mass. Double integral. Bounds stay the same, so just go ahead and drop those in if you need to. We have a y, since this is a y bar, x squared plus y squared dy dx. And that one would give us 2a over 5 as well. So, putting these together, the x bar y bar would be 2a over 5 and 2a over 5. Which is kind of convenient, and I don't know if it's so much convenient as maybe it's just something maybe that's expected with a very symmetric region like this, with a very symmetric density function. You are in fact going to have some symmetry when it comes to that center of mass, or that centroid that we're trying to find here. All right, so in this problem, we're going to find the centroid where r is going to be bounded by these two things and the density function equals y. And you know what? I need to go back and say something here. I guess I misspoke as well. Centroids and center of masses are very similar. They're related. It's to the sense of all centroids are center of masses, but not all center of masses are centroids. This is really a center of mass problem. Center of mass, because we don't have a constant density function, and that was the same in the previous as well. The density function wasn't a constant like 4 or 12 or whatever. So if we have variable density functions, then we're actually computing a center of mass. So I do want to clarify that before moving forward, even though it's just a play on words. So let's go ahead and get this thing set up again. I'm going to go ahead and start by sketching in my region. This is going to be our circle here, and we're inside of it with radius a, and then y is bigger equals 0 as well, which means we have the top half of that circle. So if we have this guy here, then I'll go ahead and sketch in that. And so what it boils down to is we're trying to find the place where we can balance this, so the center of mass. And in this case, much like the last one, due to our density function as well, we can use some symmetry. We know that this is going to balance somewhere right here along the y-axis, implying that x bar would be equal to 0. Now, if you don't believe that, you can always run through it, and that's great, but it is going to save you a lot of work by recognizing these things early on. So for us, all we really need to do is compute m, followed by then y bar. So for m, we're going to have the double integral. We're going to have our density function right here, followed by dA. Now, when it comes down to this particular picture and these functions, I do think converting this to polar is the way to go. So for example, if we're going to drop our density function in here, the y value is now going to be r sine theta, and then the dA behind it is going to be the r dr d theta. And so that keeps our function there pretty easy to integrate, but more importantly, it's really going to help us with these bounds. When it comes to the bounds, we would then be reaching out from 0 to a on the r value. So we've got a 0 to a, and then we go from 0 to pi on the theta, as this thing would sweep around 0 to pi. And so that gives us a 2a cubed over 3. So then for y bar, as we start, we'll flip that. That'll be a 3 over 2a cubed. Remember, the bounds will always stay the same. Oops, that's a 0. And then for y bar, we would need to start with a y, followed by the density function, followed by the dA, which is r dr d theta. So we're going to have an r sine theta for the y, an r sine theta for the density function, and then times an r dr d theta. And this one comes out to be 3 pi a over 16, which means that our x bar y bar would now be 0 comma 3 pi a over 16 for the final answer. So I'm a big believer in symmetry when possible when it comes to these types of problems, because the number of integrals that you will be able to kind of work around will definitely be worth saving some time.